Welcome to the AI Paper Podcast. We are diving into a really big one today, Genie Sim 3.0, a high-fidelity comprehensive simulation platform for humanoid robot.
Right.
This paper, it's really tackling the core challenge in embodied AI. How do you get enough high-quality data without, spending a fortune on real robots? Okay, let's just jump right in. Key insight number one, Genie Sim 3.0 basically digitizes the 3D artist. It's this unified platform with something called the Genie Sim generator. It's an LLM-powered tool, and it lets researchers create these incredibly complex, high-fidelity scenes just using natural language. That alone solves a huge bottleneck.
And with that kind of scale, you need a new way to measure if it's even working. So key insight number two is a total breakthrough in evaluation. They've introduced the first benchmark that uses both LLMs and vision language models, or VLMs, for automated assessment. It can generate and score over 100,000 scenarios automatically.
So no more simple pass-fail metric.
Exactly. It's nuanced, it's scalable, it's diagnostic.
And the third insight, this is the one that really ties it all together, is the validation. They're open sourcing over 10,000 hours of synthetic data. We're talking 5,140 simulation assets. And the experiments show this data provides a superior zero-shot sim-to-real transfer. It proves synthetic data can actually substitute for real-world collection. That's the holy grail.
Yeah.
So let's zoom out for a second. Why is a platform like this so necessary right now? We're all trying to build these robust vision language action models, VLA models, the ones that here put the blue mug next to the laptop and then, actually do it. And that needs just massive, diverse data sets.
It does. And real-world data collection is just cripplingly slow.
Right.
It's so expensive, and it just doesn't scale to the level we need for real generalization.
Right.
And that's really the crux of the problem. The whole embodied AI community has been hitting a wall made of three specific bottlenecks that this platform is, designed to just demolish. The first one is what you just mentioned, manual creation. To get a simulation that you can actually trust, you need 3D specialists. You need them handcrafting environments.
And that takes forever and costs a ton of money.
A ton. And it severely limits the scale and variety you can possibly get for training.
So you end up with a robot that can only make toast in one specific kitchen.
Precisely. The second bottleneck is control. We have automated generation tools, but they often just give up fine-grained control for speed. But if you're doing serious research, if you need to debug a failure or run an ablation study on, say, friction, you need to be able to reproduce a scenario perfectly.
Or vary it systematically.
Exactly. And most platforms just don't let you do that. And then there's the third bottleneck, which is, I think, the weakest link in the whole chain, evaluation deficiency. Right now, evaluation is it's fixed, handcrafted metrics. Did the block go in the box? Yes or no? It's a binary success rate.
And if that doesn't tell you enough, you have to get a person to sit there and watch it, which is slow and subjective.
It absolutely doesn't scale. It just fails to capture any of the nuance of what makes a task successful.
So Genie Sim 3.0 is coming in as this comprehensive open source attack on all three of those problems, integrating environment reconstruction, scene generation, data collection, and this automated evaluation. And they're open sourcing 5,140 assets and over 100,000 evaluation scenarios. I mean, that volume alone is just a huge gift to the community.
It really is. And to make it all work, the platform provides 5 critical new modules. There's a semantic query asset retrieval system for that massive library of objects. Then there's the LLM-powered scene generation with domain randomization built right in. The 10,000-hour dataset itself, the evaluation benchmark. And finally, the integrated platform that ties it all together.
Okay, let's get into the architecture. For me, the most compelling part of this paper is the engineering behind that LLM-driven scene generation, the Genie Sim generator. It's the part that lets you replace a 3D artist with just a simple conversational prompt.
And what's so fascinating is how they structured it. They have to manage this transition from ambiguous human language, which is messy, to the very precise requirements of a physics simulator. The whole thing is broken down into 4 technical LLM-driven stages. It's like a chain.
Okay, so walk us through that chain. What happens first when I tell the system, put some randomly stacked red blocks on the wooden table?
So stage 1 is the intention interpreter. This is where a chain of thought or COT enabled LLM really proves its worth. It takes your vague phrase like some blocks are randomly arranged, and it has to translate that into a structured JSON schema.
A blueprint.
Exactly. It's a blueprint that specifies object classes, constraints like size or color, and critically those precise spatial relations like on top of or next to.
It's basically denoising the human request before it hits the database. That structured output has to be the key, which I guess moves us into stage 2, right? Accessing the asset.
Right. That JSON schema goes straight to the assets index. And this part is built on Retrieval Augmented Generation, or RAG. They took all 5,140 objects and encoded their descriptions into these high-dimensional vectors.
And stored them in a vector database.
Yep, it acts like this lightning-fast catalog.
Why RAG, though? Why not just a simple keyword search?
Generalization. It's all about generalization. If you ask for a can of soda, you don't want a system that only finds things literally named Coke.
Right. You want it to understand the concept of a soda can.
Exactly. So, by using vector embeddings and cosine similarity, when a request for a drink container comes in, the system instantly pulls the top CAG most semantically similar objects. It could be a soda can, a water bottle, a mug.
And it gets all the metadata, too, like the USD paths and collision data.
Everything it needs. And it does this in about 200 milliseconds.
That speed is so important if you're trying to generate thousands of different scenes, and then that leads to the actual code creation.
Stage 3. The DSL code generator. Another LLM takes the interpreted intent from stage 1 and the assets from stage 2, and it synthesizes precise Python code using their own domain-specific language, their DSL. This DSL is really the magic component. It's what gives you that fine-grained control. By feeding the asset context directly into the prompt for the code generator, the system can generalize over categories, poses, even lighting and textures.
Without needing a human to go in and tweak things for every new scene.
Right. It just turns the whole process into a rapid assembly line.
And the final step is actually building the scene from that code.
That's the results assembler. It just takes that DSL program and runs it. And to get that variety we need for robust training, the domain randomization, it applies random functions to all the variables. Poses, layouts, colors, lighting. It then uses standard tools like OpenUSD and Isaac Sim APIs to generate the final simulation-ready USD files. This whole 4-stage pipeline lets them create thousands of diverse scenes in just a few minutes.
Okay, so we've got the scenes, but the big question is always, are these LLM-generated scenes actually photorealistic enough to bridge that famous sim-to-real gap? If the fidelity is low, none of this matters.
Fidelity is everything for sim-to-real. So they start with a really meticulous reconstruction pipeline. They use 3D Gaussian splatting, 3D-GS, which is a state-of-the-art neural rendering tech. And this is key because it gives them both the photorealism for the vision models and the high-precision meshes that you need for the actual physics simulation.
I remember the paper mentioned a classic problem with 3D-GS, especially indoors where it's cluttered. Getting that perfect pixel-level camera pose accuracy is really hard. How'd this solve that?
Yeah, that requires some pretty advanced feature engineering. To stabilize the camera poses, they enhance their feature extraction using techniques like superpoint and light glue. This helps them find good features even in places with bad lighting or weak textures. Then they do this complex bundle adjustment optimization using prior data from LiDAR SLAM to make sure the virtual camera lines up almost perfectly with the real one.
And they also have a solution for when they don't capture every angle in the real world, right? How do they fill in those gaps?
They use generative models as a safety net. If their initial data collection is sparse, they deploy a generative model to sort of extrapolate and render new views. It creates synthetic, high-quality images to fill in the missing perspectives before the final 3D-GS training.
That's really clever. Okay, let's pivot to what I think is maybe the most groundbreaking part for researchers, the automated evaluation pipeline using LLMs and VLMs. We already said manual scoring doesn't work at scale. So how does this system handle a complex command like organize all the pens in the blue cup on the left side of the desk?
It creates this fully automated diagnostic pipeline. First, an LLM combined with a system they call the Action Domain Evaluation Rule, or ADOR, automatically generates tons of reasonable task instructions. And it also generates the evaluation configuration files that go with them. So the system is essentially writing its own tests.
The LLM writes the test, but how does it get the score without a human watching?
That's the really brilliant part, the VLM automated scoring. They give a vision language model the full task instructions and the video feed from the robot's execution. And because the VLM has this powerful visual and semantic understanding, it acts like a super detailed, tireless human QA tester.
Can you give us a concrete example of that nuance?
Sure. Let's say the task is place the black marker in the pen holder and close the laptop lid. A simple binary score would just say fail if the lid is still open. But the VLM checks multiple specific checkpoints. It can look at the final scene and report back, yes, the black marker is in the pen holder, and no, the laptop lid is still open by about 15 degrees.
So it gives you evidence-based justification for why it failed.
Exactly. You get diagnostics, not just a pass or fail. This immediately speeds up the debugging process for any researcher.
And it's evaluating multiple things at once.
Yes, a whole capability profile.
Yeah.
Semantic understanding, did it know a marker from a pen? Spatial reasoning, did it go to the left side of the desk? And operational execution, was the grasp stable? It defines the model's limits so much more clearly.
Okay, let's talk about the dataset itself. 10,000 hours of synthetic data across 200 tasks is just monumental. How did they manage that volume? Must have been a dual strategy.
It was. They use a dual-mode data collection pipeline. The first mode is teleoperation. They use a PICO VR headset to let a human operator control the robot in the simulation. This is absolutely crucial for getting those high-quality, human-like demonstrations for really complex, long-horizon tasks, the kinds of things that are almost impossible to script.
And then the second mode is where the automation and the real scale comes from.
That's the automated collection. It's super efficient. It uses Curabo, which is a GPU-accelerated motion planner, as its core engine. This lets them generate successful trajectories for simpler tasks at a massive volume.
But what about when the automation fails? Simulations can be finicky. What safeguards did they build in to make sure the data quality is still high?
That's a critical piece of the engineering here. When parsing a task, they don't just generate one action sequence. They use GraspNet to derive candidate key waypoints, and they form multiple alternative action sequences from those. And here's the clever part: the robust retry mechanism. If one sequence fails, the system performs a state rollback to the last successful point, and then it just tries the next candidate sequence. This really maximizes the success rate. That's smart. And I also want to point out a design choice they made about scene complexity. A lot of systems simplify scenes by removing objects that aren't part of the task just to avoid collisions. But Genie Sim 3.0 keeps the full, cluttered environment. To make that work efficiently, they apply mesh simplification to the objects during initialization. So you get the realism of a cluttered scene, but the planning is still fast.
Which preserves that real-world complexity while still being scalable. And they organized all this data with a clear taxonomy. How should a researcher think about that structure?
The taxonomy is designed for logical progression. It's structured along three axes. The first is manipulation skill. These are your basic motor actions: pick, place, pull, open, close. The second axis is cognitive comprehension. This is about interpreting abstract instructions. Can the model understand spatial reasoning like left of or under? Can it recognize colors? Does it have common sense?
And the final axis is just the scope of the problem.
Exactly. Task complexity. Is it a short horizon task or a long one? Single arm or bimanual? This hierarchy lets you incrementally increase the difficulty and systematically test for generalization.
Okay, so we have the generation, the fidelity, the scale. Now for the ultimate test, the sim-to-real validation. This is where they answer the big question. Can synthetic data actually replace expensive real-world data?
Right. To quantify this, they ran 32 groups of experiments. They used a standard VLA model, the Pi 0.5 base model, and deployed the trained policies on a physical Agibot G1 robot. They picked 4 representative tasks, things like select color, grasp targets, organize items. So a good mix of basic skills and cognitive challenges.
And they compared 4 different training setups.
Yes, 200 episodes of real data, 500 episodes of real data, 500 episodes of synthetic data, and then a massive set of 1,500 episodes of synthetic data. They were looking for that crossover point where scale beats raw fidelity.
So what happened in that first head-to-head, the 500 versus 500 test?
The results there were pretty much what you'd expect.
Huh.
The model trained on 500 real-world episodes consistently did better than the one trained on 500 synthetic episodes. And that's because real data still captures complex physics contact, friction, visual noise with slightly higher fidelity.
Yeah.
So in a one-to-one comparison, real data had the edge.
But then it all changes when they ramp up the scale of the synthetic data. This is the crucial finding for anyone building a generalist robot.
Absolutely. When they tested the zero-shot success rates in the real environment, the model trained exclusively on 1,500 episodes of synthetic data got the highest success rates across all 4 tasks. This is huge. It empirically validates the paper's core idea. Massive scale synthetic data, when you combine it with systematic domain randomization, can effectively overcome the sim-to-real gap.
So the diversity and scale you get from synthetic data is actually more important for generalization than the slight fidelity advantage you get from a smaller real-world data set.
It makes synthetic data a pragmatic, scalable, and maybe even a superior choice for these generalist models.
And finally, they had to prove that the simulation itself is a reliable tool for researchers. How consistent were the results between the simulation and the real world?
They did a detailed analysis, and despite those minor discrepancies we talked about, like approximations of friction, the overall performance trends were remarkably consistent. The quantitative analysis showed a statistically significant, strong positive relationship. They got an R-squared value of 0.924.
And for anyone who's not a statistician, what does that mean in practice?
It means that if your model performs terribly in their simulation, you can be very confident it will also perform terribly on the real robot, and vice versa. That kind of predictive power is why this platform is such a game changer for accelerating research.
So to wrap up this massive paper, Genie Sim 3.0 has given us the LLM-driven Genie Sim generator to democratize scene creation, a scalable VLM-based evaluation pipeline for diagnostics, and the empirical proof that large-scale synthetic data is the most effective path to zero-shot transfer. They've really provided the tools for the next generation of VLA models.
And given that evidence that 1,500 episodes of randomized synthetic data beat 500 episodes of real-world data in the real world, it raises a really important question for all of you working on your next model. Will the primary bottleneck for building truly generalist robots be the fidelity of simulation physics? Or have we entered an era where the only real limit is the sheer amount of compute needed to generate enough diverse, randomized synthetic data to train for every possible scenario? That's something worth mulling over as you design your next data pipeline.